Okay, so course 5 of probability and statistics, and we are going to start with exercises, and more precisely the exercise 16 of the list 3. Okay, that is this one. So during the previous session we have started to see some particular distribution in the discrete case, okay? And this week we are going to finish this part of the course and also do exercises. Okay. So exercise 16. So I suppose that I have two independent random variables, x and y, and both follow a uniform on the set 0, 1, 2 until n. Okay? So, using my notations, x and y are independent as random variables, okay? And I suppose that x and y follows a uniform on these finite sets. Okay? So first of all, I know that the possible values for x and y are in this set, okay? And what can you say about this probability? What is the probability that x is equal to k? That is the same in the probability that y is equal to k. What is this probability? So be careful. When you have a finite set, okay, the uniform probability is the one that gives the probability 1 over the number of elements to each element of my set. How many elements here?
N plus 1.
N plus 1, not n. I start from 0. 0, 1, 2, n. Okay? Be careful, 1 over the total number of elements, and here I have n plus 1 elements. Okay? So it should be possible to do exactly the same exercise with the uniform on 1n, but it's not the question of the statement. Okay? And I am interested in the computations of two probabilities. First, the probability that x is equal to y. And before to be able to compute the probability of this set, we have to understand what is a little bit this set. So do you have an idea what to do? We have several possibilities to do. But I repeat that the general idea when you have a probability to compute, okay, first of all you have to understand what is this set. In fact, what is the set x equal to y? And I remind you that this is the notation for the set of the W belonging to the universe such that xW is equal to yW. And I have a statement, that tells me that I know these probabilities and I know that they are independent. Okay? So to start, ready? Okay, so one possibility to see this is to say that, okay, what are the possible situations? I know that my two random variables take values in 0, 1, 2, n. They will be equal if they take the same value. That is, they are both equal to 0, or they are both equal to 1, or they are both equal to 2, and so on. Okay? So one possibility is to write this as a different union I have heard a little sound, okay, and I don't want. Just check that the record is okay. Okay, it seems to be sure. So, disjoint union from k equal to 0 to n. We'll take mine. I have always my pocket. Okay, of what? Of x equal to y equal to k. Okay? For two quantity to be equal, okay, they just have to take the same value, and since they have values between 0 and n, okay, they have to take the same value between 0 and n. So it will be x equal to y equal to 0, or x equal to y equal to 1, or x equal to y equal to 2, and so on. So do you agree with this one? And I have here a disjoint union. From the definition of a probability, I know that when I have a disjoint union, here it's a finite disjoint union. The probability of the disjoint union is equal to the sum of the probability. Okay? So the probability I am interested in can be written as the sum from k equal to 0 to n of the probability that x is equal to y is equal to k. Do you agree? For the moment, I have used nothing. The only thing I have used is the fact that they take values in 0, n. I don't have used the independence. I don't have used the fact that they follow uniform, okay? So it's something that can be written in grid generality, okay? The only thing I have used is the fact that I am between 0 and small n. What can I say now? Because I want to continue my computation. Now we are going to start to use by the statements. Sorry?
X equals k, y equals k.
And y equal to k. Okay? I am agree with you that this may be written as x equal to k and y equal to k. They are both equal to k if the first is equal to k and the second one is equal to k. And why it's interesting to write the thing this way? Because I have the probability of an intersection and I have an hypothesis in my statement, that is, they are independent. Okay? So all the related pre-images are independent, in particular this one, the probability of the intersection is equal to the product of the probabilities. And here, I use the independence to write this. If they are not, I can't continue a priori this way. Okay, if they are not independent, I need more hypotheses to be able to do this computation. But here they are independent. And now, continuing to use my statement, I know what are both probabilities. Each of them is equal to 1 over n plus 1. So it means that by the uniform hypothesis now, that this product is simply equal to 1 over n plus 1 square. Okay? Here I use the uniform hypothesis. And at the end, what is the probability I am interested in? It's the sum over n plus 1 elements of the constant term 1 over n plus 1 square. What I will obtain, so it means that I do 1 over n plus 1 square plus 1 over n plus 1 square plus 1 over n plus 1 square, n plus 1 times. So how many at the end? It is just the number of terms in my sum multiplied by the value of my constant term and I obtain 1 over n plus 1. Okay? So the probability that two uniform on 0n that are independent are equal is equal to 1 over n plus 1. Okay? And the idea, and the main idea, is to express the set I am interested in, okay, to try to decompose it, okay, in order to make a clear intersection, and then I am able to compute their probabilities because they are independent, and I know the probability of each of them. Okay? Is it clear for everybody, this little kind of reasoning? So if it's clear, I give you 5 minutes to do by yourself the other one. Okay? Here, it's the probability that they are equal. Now, the probability that they are less. X is less than y. Okay? And in fact, I will check for attendance now. Okay? I give you time to do this. Okay? So I just put. So we have to compute the probability that x is less than y. Of course, the only thing I can use is this one I have in the statement. An idea how to do?
X less than or equal to k and y less than or equal to k.
Okay, so you can try to use more or less the same idea. Okay, that is, but to see what happened, it's exactly what I have done here. In fact, to see what happened when y take a particular value. Okay, so if y is equal to k, then in order to have this inequality, x will be less than k. Okay. So it is possible exactly to do as previously, that is to use the decomposition this way. But here, it's something that can be also used in this situation, but I prefer to use, in fact, it's the same idea, but in order to remind a result from the course. The idea is that what you want to do is you take in consideration different cases depending on the values of y. And in fact, when you do this, there is a result in the course that do exactly this one. Which one? You have a result in the course that tell you in order to compute the probability, you may know, okay, some related probabilities, and then you do a sum, and at the end you obtain the whole probability you are interested in. The law of total probability. Okay? But you know that if I want to use the law of total probability, I need a partition. And what will be my partition? But exactly what you say, that is, I will consider the different possible values for y, and in this way I will obtain a partition, and it will be possible for me to apply the law of total probability. Okay? So in fact, it is two kind of way to do this kind of exercise. Okay? But you can invert the solutions, okay, to obtain the same result. So I say the following: y equal to 0, y equal to 1, until y equal to n. I have here a partition of the universe because I have the set of all the possible values. Okay, so I can recover the whole universe. And I know that they are pairwise division because for a mapping it's not possible to take two values at the same time. Okay, so you have here partition of the universe. And since I have a partition of the universe, I can use the law of total probability that tell me that the probability that x is less than capital Y may be written in this situation as a finite sum. Okay, so we start at 1. Yeah? This one of what? The probability that x is less than y, given that y is equal to k, multiplied by the probability that y is equal to k. Okay? Of course, for this formula, if I put instead of less equal, you have this formula and you recover exactly what I have done this here. Okay? Okay. So I need to compute, okay, the two probabilities involved in this sum here. So what is this one? We have calculated that or not? But you calculated, no. We have more than this. We have it in the statement. Y follows a uniform on the set 0, 1 until n. So it is 1 over n plus 1. For this one here. So it's a conditional probability. So I have an extra information that is y is equal to k. So since y is equal to k, I can replace it in this set here. Y is equal to k. So this probability is just the probability that x is less than k, given that y is equal to k. I just replace y by the value I know now because I deal with a conditional probability. What can I use now? For the moment, there is an element in my statement that I don't have used. Which one? Independence. And I know that when two sets are independent, the conditional probability is none other than P of A given B is equal to what when they are independent? P of A. P of A. Okay? If they are independent, the probability is the same as the conditional probability. So using the independence, so here I use the independence and I obtain the probability that x is less than k. And now the only thing I have to know before to do a little computation is what is the probability that x is less than k here. Knowing the fact that I know the distribution of capital X. What is this? If I am less than k, what is the meaning of my possible values? Hmm? 0 to k. Can be 0, 1, 2, until k. Okay. How many possibilities? So to be less than k? K plus 1. I have the k plus 1 first number here that are okay in order to check this condition here. And what is the probability of each number to occur? 1 over n plus 1. Okay, so I can take k plus 1 different values. Okay, the probability of each of them being equal to 1 over n plus 1. So I obtain here k plus 1 over n plus 1. Is it okay for everybody, this? If it's not totally clear that this way, you can also say the following. That x, it's exactly what I have stated, that x less than k is what? It's the disjunct union from I equal to 0 to k, x equal to I. It's exactly what I have said. To be less than k, I can be equal to 0 or equal to 1 or equal to 2 until k. I have pairwise division set. The probability of the union is equal to the sum of the probabilities. knowing the fact that the probability of each of them is equal to 1 over n plus 1. That's why I obtain exactly this term. So this, if you are not okay with what I have written here, it may be explained by this equality here, using once again the additivity of the probability with respect to pairwise division sets. Okay? So now the part concerning the probability is finished, but I have a sum to compute. Okay? So I have a sum to compute. We have obtained that the probability that x is less than y is equal to what? So I summarize what I have obtained. It's the sum from k equal to 0 to n of what? Of k plus 1 over n plus 1 square. I can remove the 1 over n plus 1 square from the sum because it is something that is independent of the index k. And I have this sum to compute. The question now is, what is this sum? The sum from k equal to 0 to n of the k plus 1. So another way to write it, you see that I have inside my sum k plus 1. My index is k, so I can do a change of index. I can define a new index to be k plus 1. If I do this, I can express this sum as the sum from k equal to 1 to n plus 1 of k. Just I do a translation in my sum, okay? I change my index in order to obtain this, as we have already done together, because I have k plus 1 here, and I put, in fact, a new index, that is this one, and I change my set of indexation because my new index becomes k plus 1. So you have the sum of the n plus 1 first integers.
N plus 1, n plus 2.
So it's something that is in the summer list, okay? Something that is in the summer list. It was, if I remind, it was in the summer list, a little exercise concerning induction. Okay, I have asked you to prove by induction the fact that I have this. So from the summer list, you have the fact that the sum from k equal to 0 to n, k is equal to n plus 1 over 2. I am interested with the same sum. The only thing that is changing is that I have n plus 1 instead of n here. So if I continue here, I obtain what? So the first term here, that is 1 over n plus 1 square. And this sum, so I have just to replace in this expression here n by n plus 1, and I obtain here what? N plus 1, n plus 2 over 2. That may be simplified as n plus 2 over 2 n plus 1. Okay? So this is the probability that a uniform on the set 0n is less than another uniform that is independent. Okay? Now it's just computation. The probabilistic part, okay, is here, for example, to use the law of total probability, to use the independence, and to use the fact that they have a known distribution. Okay? And you will see that the use of the law of total probability this way in order to do computations in the case of discrete random variable will be something that we are going to do again. Do you have some questions concerning this? Okay? So an application of the law of total probability in order to decompose this set, okay, this way, and using the fact that I have independence and non-probability. Okay. So no questions? Is it clear for everybody? Okay, so let's do another exercise. The exercise 8 of the list 3. This one here. So I repeat the last time, are you okay with my solution? Yeah? So it's kind of computation we are going to do several times again, okay, this week. May I erase? I erase. Now it's the exercise 8 of the list 3. So what you have here? You are in the following situation. So you have a box with capital N balls that are numbered from 1 to capital N. Okay? You choose N ball, small n balls at random, okay? With replacement. So you choose 1, you see the number you obtain, you put it back in the box, and so on. Okay? I did not, so I do this small n times. Okay, and I have capital N balls. I denote by capital X the greatest number I obtain, and by capital Y the smallest. What we want to do in this exercise is in fact to compute the distribution of capital X and capital Y. It's my aim. Okay? But it may be complicated to do this directly. And I will explain to you why just after. So you have, okay, an intermediate computation to do in order to deduce the distribution of these two random variables of interest. So I erase this. So I do small n drawings. Okay? I do this. I do one, I put the ball back. Okay, I do one other, and I just, okay, copy the number I obtain, and at the end I take the max of all of them. So if I want to write the things, okay, in a compact way, I can introduce notations here. Because I do small n drawings, okay, and each time I will obtain a number between 1 and capital N. Okay? So we can define the following. For I between 1, okay, and small n, but you can define capital Xi, the number you obtain, at stage small I. Okay? X1 is the number I obtained for the first time. So for I between 1 and n, okay, we define Xi, the number you obtain at stage I. Okay? Okay, so X1 is what I obtain in the first drawing, okay? That is the number between 1 and n. X2, what I obtained during the second one, that is also a number between 1 and n because I do this with replacement, okay? Are you able to express, so I am interested in capital X and capital Y, capital X being the greatest number I obtain and capital Y being the smallest. Are you able to express capital X and capital Y using what I have defined on the board here? don't say that it is difficult, I have introduced this just in order to be able to define capital X and capital Y in a compact way. So, with what I have defined, X is equal to the maximum of the xi, okay, and y is equal to the minimum, okay? So I have defined the random variable capital Xi. What can you say about these random variables? This one. So you choose one number and then you put it back and you choose another one. What can you say about them? Independent. So they are independent, okay, because I choose something, okay, and after my choice, I come back to the initial situation to do it another time. Okay? So, x1, xn are independent. And what can you say about the distribution of each of them? At stage I choose one ball among capital N. Uniform, okay. On which set? Uniform on which set?
1 to n.
Which n? Because I have two n here, small n and capital N. Yeah, capital N. I'm agree. So in fact, if I want to translate the statement with words, okay, your job here is to find the distribution of the maximum and the minimum of small n independent uniform on the set 1 capital N. Okay? It's what I want you to do. So in particular, for this one, it means that for all I belonging to 1n, for all k between 1 and capital N, the probability that xi is equal to k is equal to what? So I have a uniform on this set. What is the probability for each element to occur? 1 over the total number of elements, and here it's capital N. Okay. I have this one. So here for the moment I have said nothing. I have just translated the statement, okay, in order to have something that is clear. In fact, I have all this information in my statement. Okay? So I say you that my job, in fact, in this exercise is to compute the distributions of these two random variables, to find what are they. What is the set of the possible values for this one? What are the possible values for the max and for the mean? N, wait, yeah, 1, 2, 8, okay? So this one belongs to 1n, and this one also. Because I take the max or the mean between numbers that are between 1 and capital N. Okay? So if I want you to find the distribution a priori of capital X and capital Y, then you have to be able to find the probability that X is equal to 1, the probability that X is equal to 2, the probability that X is equal to capital N, and the same for capital Y. Okay? But if you do this way, it is possible to do directly, okay? But it is a little bit complicated because what is the meaning of the maximum is equal to, let's say, 3? It's complicated to describe because, okay, you may have you are sure that you don't take values that are strictly more than 3, for sure, okay? So it's just values between 1, 2, or 3. But 3 can be 1 time, 2 times, 3 times, or capital N times, and for the other it can be 1, 2. So I have, in fact, not a lot, but several cases to consider. But it may be a little bit complicated to do this way because I can do confusion. I can count even twice, okay, or I can forget some evens. So when you have a maximum and a minimum to deal with, okay, to try to find maximum equal to someone or minimum equal to someone is not the good way to do. It's not the good way to do because I repeat, to describe perfectly what is the event maximum equal to something or minimum equal to something can be a little bit complicated. It's possible to do, of course. Huh? If you are clear, okay, it's possible to describe everything, okay, to have a good description and to be able to compute the things. So that's why we are not going to do this way, but we are going to compute the distribution to do intermediate steps, okay? So my first question will be compute the probability that capital X is less than small x, okay, for x belonging to 1. So try to do, I give you 5 minutes to do by yourself. To compute this one. So I have the probability that the maximum is less than small x to compute. Okay? And why it's easy to compute this one? Because I have the max here. And in fact, if you have different numbers, you can say that the maximum is less than small x, okay, if and only if they are all less than small x. To say that the maximum is less than small x, okay, is equivalent to say that they are all less So it's something that has nothing to do with the probability. Okay, so if you have a finite number of numbers, okay, you can say that the maximum is less than 2. Okay, if and only if they are all less than 2 in the large sense. Okay, so it's not product, it's intersection here.
I said probability, so maybe if you put probability, then you have to multiply all of them from the
Yeah, okay. So I am agree to say it this way. Okay. Does everybody agree with what I have written here? So the last time, huh? So the maximum is less than x if and only if they are all less than small x. It's exactly what I can translate by this set is the intersection of all these ones.
What is the small and not capital N?
Why?
Not capital N in intersection.
Because I do small n drawings. Capital N is just, okay, the number of balls I have in my box. What you do here, you choose small n times, okay? So I choose small n times balls, okay? And I want that the result of each drawing is less than small x. I have small n drawings and I want all of them less than small x. Okay? So I repeat that this is true because you have here something that is the maximum. If you change it with the minimum or you change it with something like it doesn't work. The max is less than. Okay, so when you have maximum to deal with, okay, it's not that complicated to describe what is the set maximum less than someone. Okay? Equal is more complicated. Greater is more complicated. Okay, but less, you know that they all will be less than small x. I repeat that it is something that has nothing to do with probabilities. Okay? So now, as I said, I have an intersection to compute. The probability of an intersection. I am okay to do this when I have independence. So using the independence, the probability I am interested in is the probability of an intersection that becomes the product of the probabilities because they are independent. Okay? So using independence here, using independence, I can write the probability of the intersection as, so the product of the probability with this symbol that is the product. Okay? But here intersection and capital pi here from I equal to 1 to n, okay, is the product symbol that is the same as the sum, okay, but for products. Okay. It's just that it is the probability that x1 is less than small x times the probability that x2 is less than small x times the probability that x3 is less than small x, and so on, until the probability that x small n is less than small x. Okay. And now if I want to compute what I am interested in, I need to be able to compute the probability of each term here. Okay, it's xi here. So what is the probability that xi is less than small x? We know that the xi are independent, and I have used this, and I know that xi follow a uniform on one capital N. So what is the probability that you are less than small x, knowing that x is between 1 and capital N here? What is the probability that xi is less than small x? Well, this is the probability that xi is equal to 1, 2, 3, until small x. Okay? How many cases? Small x cases. What is the probability for each case? 1 over capital N. So at the end, I obtain what here? Okay, so it's the product from I equal to 1 to small n of small x over capital N. And I see that here I do small n times the product of the same quantity. So it is x over capital N multiplied by x over capital n times in the product. Okay? And so I can express this using a power. This one. Using the fact that I have the products of small n terms, okay? Each of them being equal to small x over capital N. So it is the first part of the question small a here. And then the second step of the question is what I have in mind at the beginning, but that was a little bit complicated to do directly. That is to find the distribution of the random variable capital X. That is now what I want. I want for all x belonging to 1 n, I want the probability that x is equal to small x. It's what I want now. what I have in mind to compute from the beginning, okay, but I have said to you that express this event is a little bit complicated. That's why we pass from this one. And the only question is how to make the link between what I want to compute and what I have computed. So it is a formula that is in the course, okay? But it is also something that you can recover basically. It's a formula we have seen together. I will show you in the course to show you that it is inside. That is the formula in blue here. The formula in blue that you can recover in the discrete case the probability mass function from the distribution function. Okay. Here, my set of possible values, that is the xi, are just this one. Okay, this one. And so the probability mass function here can be defined as the probability that x is less than small x minus the probability that x is less than x minus 1. Here, the previous term, since I have in this situation, is x minus 1. Okay? And now it's finished, because I am able to compute both of them, because I have done my preliminary computation here. So keep in mind that even if you forgot what I have written in blue here, it's something that is very easy to recover. Very, very easy to recover. Because, I erase this one, the formula in blue in the slides, okay, just means, so if I adapt it to my problem here, just say that, to say that x is less than small x in my situation here, is just, okay, x is equal to small x, disjunct union with x is less or equal than x minus 1. Because my set of possible values is just 1, 2, 3, x minus 1, x, and so on. Okay. And so, the probability of this one is equal to the sum of these probabilities, from which I deduce this one. So you can know how to recover the probability mass function from the distribution function in the discrete case, or have in mind that it is not a complicated result that you can recover in one line, in fact. Okay? Writing this one implies this one here, because you have a disjunct union here, so the probability of this one is the sum of these probabilities. And now I just have to plug. Question? Sure? I just have to plug what I have obtained. So it is x over n to the power n minus x minus 1 over n to the power n. Okay? And it's a good exercise to try to compute, or to try to compute at home this probability directly. You see that the result is not that easy. So if I want to compute directly, that is to describe directly what is the event, the maximum is equal to someone, I have things to say to obtain at the end this one. That seems to be not that natural. Okay? So, if you have one thing to keep in mind, maximum is less, they are all s, all less, it is equivalent, okay? See, I have numbers, the maximum of these numbers will be less than someone if they are all less than small than this someone. It's an equivalence. Okay? So here you have an example where it is easier to compute the distribution function than the probability mass function directly, but we can recover it from the formula in blue here, or if I have in mind the little relation I have written on the blackboard. Well, try to do the same for the minimum by yourself. Okay, now I am interested in the minimum. So concerning the minimum, okay, once again I want to compute the distribution, that is the probability that y is equal to small x, but to do this I have an intermediate step, that is to compute the probability that the minimum is greater than x because y greater than x can be written easily as they are all greater than x. So we are going to use this one to use the independence. So the probability of the intersection will be the product of the probabilities. And you have to compute this probability here, knowing the fact that it belongs to 1n, and here x belongs to 1n for sure. So what is the probability that xi is greater than x? So the possible cases are xi is equal to x, xi is equal to x plus 1 until xi is equal to capital N. How many cases here? Yeah. So I have, okay, the numbers between x and capital N are, okay, I have capital N minus x plus 1 number between small x and capital N. We have 1, 2, x, n. Okay? How many numbers between x and capital N? I have n minus x plus 1. Now why? Because here, okay, I have exactly x minus 1 number for a total of capital N, in fact. Okay? So to say that I am greater than x means that I am equal to x plus 1 or x plus 2 or capital N, and I have n minus x plus 1 possibilities, each of them having a probability of 1 over capital N. So the probability that xi is greater than x is 1 over capital N multiplied by the number of positive cases. Let's say that is x plus 1 capital N, n minus x plus 1. Okay? N minus x plus 1 over capital N. Once again, here I have a product with small n terms, okay? What I have inside is a constant, so I will just make the power appear. The power n. Okay? So it's exactly in the same spirit here. The only thing that you have to keep in mind in the case of the mean here is that the minimum is less than, is greater than, if they are all greater than. Maximum less than, they are all less than, okay? Minimum greater, they are all greater. In the two cases, this is an equivalence. Okay? So I have this one. Do you have questions? It's clear for everybody? So if it is, at the end what I have to obtain, I want the probability that y is equal to small x. And I want to obtain it from this one here. It's a kind of the analogous of the formula we have used previously. That was the formula giving to me the probability mass function from the distribution function. So here, how to obtain this probability from these ones here. What is the probability that y is equal to small x if I want to express it using this kind of probabilities here? I can say that it is the probability to be greater than x minus the probability to be greater than x plus 1. And what I use, in fact, if I say this, I just use the fact that y greater than x plus 1 union y equal to x is equal to y greater than x. The probability of this one will be the probability of this set minus the probability of this one. Okay? And so I have just to plug. It is n minus x plus 1 over capital N to the power n minus what? Minus n minus x over n to the power n. And once again, it's a good exercise to try to obtain at home this probability mass function, but doing the job directly, trying to describe perfectly what is y equal to x, and you will see that it's not that easy in order to obtain it. Okay? So in this exercise, okay, when you have to deal with the max, think about the max greater than term 1. When you have to deal with the mean, think about the mean is less. Max is less and mean greater. Okay? In the case of continuous random variable, we will see the analogous of this result, and you will see that the idea will be basically the same. Okay? So for the max and the mean, okay, in general, we don't do the problem directly. Okay? We use distribution function, or by this one, that is the 1 minus the distribution function of some 1. Okay? Maximum less, they are all less. Minimum greater, they are all greater. Okay. So a last little exercise, and after I will do the break, and I will continue the course after. Are you okay with this exercise? Yeah? Allez, to conclude with the exercise for the first part of the course, but something that may be very short if you have the good idea. A little bit less if you don't have the good one. So it's the exercise 22. So you are going to see that in this course, we work with particular distribution. So for the moment, we have seen particular distribution in the discrete case. Poisson, binomial, geometric, uniform, and so on, okay? In the continuous case, we will see other type of examples, exponential, Gaussian, and so on. And you will see that for some families, we have the following nice property, that is, if you do the sum of two independent random variables with a particular distribution, sometimes the sum, okay, has the same distribution as the previous one, or lies in the same family, let's say. Okay? So in the list 4 of exercises, you will see that if I do the sum of two Poisson distributions that are independent, okay, the distribution of the sum is a Poisson distribution with a parameter that is the sum of the parameters, something that we are going to prove in the list 4. And here, you are in the framework of binomial distribution. So binomial distribution, but with the same p. Okay, so you have a binomial distribution of parameter n1p, a binomial distribution of parameter n2p, okay, the same probability p. And I want you to prove that the sum is also, so when they are independent, the sum is a binomial random variable with parameter n1 plus n2 and p. Okay? So it's the exercise 20. So if you have in mind the result we have seen together during the previous session, it will be that easy to prove this. If it's not the case, okay, the computation are possible and not that complicated, but a little bit more tricky. And I will show you the easy way to do this. So I remind you that the binomial was defined this way in the course. Okay? So my job is to do the following, so I can write the statement in a very compact way. I have x and y that are independent. X follows the b n1 p. Y follows the b n2 p. I want you to prove that x plus y follows the b n1 plus n2. Okay? So a priori, if you come back to the slides, I have to prove. So, what is the set of the possible values for capital X? What is the set of the possible values for capital X? 0 and 1. So 0, 1, 2, and 1. What is the set of the possible values for Y? 0, 1, and 2. So if I do the sum, what is the set of the possible value for the sum? I do the sum of a number between 0 and n1 and a number between 0 and n2. What I will obtain? 0 and n1 plus n2. Okay? So 0 and 1 plus n2. Okay. And if I want to prove what I want to prove, using the definition you have on the slide, okay, so what I have to prove is that for all k belonging to 0 n1 plus n2, you have to prove that the probability that x plus y is equal to k is equal to c n1 plus n2 k p to the power k 1 minus p to the power n1 plus n2 minus k. It is a priori what you have to prove. Just the definition you have on the slide. Okay? It's possible to do the job directly, exactly using what we have done in the first exercise we have done together today. We can say that, okay, the sum is equal to k. What is the meaning of the sum is equal to k? But the sum is equal to k means that x is equal to 0 and y is equal to k, or x is equal to 1, y is equal to k minus 1, or x is equal to 2, and so on. Okay? In other words, in fact, it's the use of the law of total probability. Okay? You can do this directly using the law of total probability and compute the sum you obtain. Okay? It's one way to do. You can try to do it at home in order to handle the definition of the binomial and the law of total probability. So I repeat, try to compute at home this probability in order to obtain this one using the law of total probability. Using as a partition, for example, the set of the possible values for capital Y. Okay? Exactly as I have done in the exercise 16. It's not the way we are going to do, but it's one way to do doing computations. The way we are going to do, use the intuitive definition I have given to you of what is a binomial. So it's what it is written in the slide for the example, okay? So it's something we have already seen together. You flip an unfair coin n times and you count the number of heads you obtain. Okay? And we have seen together that it is a binomial. Another thing we have seen together is that a binomial of parameter n and p may be seen as the sum of n independent Bernoulli of parameter p. So, what we have seen together is the following. If x1, xn are independent Bernoulli of parameter p, then I have proved it by induction. Then x1 plus xn follows a DNP. Okay? So it is an equivalent characterization of what is the binomial distribution of parameter n and p, just is seen as the sum of n independent Bernoulli of parameter p. If you have in mind the example here, it means that if you define x1 as 1 if I obtain a head and 0 otherwise, if you want to count the number of heads, you just have to do the sum, okay, of this variable, taking the value 0 or 1. So if I have this in mind, in fact it's finished. Why it's finished? Because my Bn1p, okay, so if I consider, let's write it this way, I consider x1, xn1, okay, independent, BP, and I consider y1, yn2, independent BP, that are also independent of the previous one. Okay, I am in this situation. Okay. What can I say? I can write the following, that x1 plus xn1 plus y1 plus yn2, okay, that can be expressed in two ways. Here you have independent random variables from the fact that the x are independent, the y are independent, and the fact that this one are independent of the previous one. So I have a set of independent random variables here. Okay, so you have here n1 plus n2 independent BP. n1 plus n2 independent Bernoulli of parameter p. So at the end, what is the distribution of the whole sum here? But you have the sum of n1 plus n2 independent Bernoulli of parameter p. From this result here, you have a binomial of parameter n1 plus n2 p. So if I do the sum of all of them, they are independent random variables following the Bernoulli of parameter P. From the result that is in the box and that we have put together during the previous session by induction, this sum follows a binomial of parameter by the number of terms in my sum, P. Okay? But in fact, I can also cut my sum into parts. When I do this sum, I can also do the sum of the n1 first term, and then the sum of the other. What happened for the n1 first term? But I know that I have the sum of n1 independent Bernoulli of parameter P. So I have here something that follows the B n1 P. The same all for this one, where I have a B n2 P, and from my statement they are equivalent, they are independent. So one way to prove this is to have in mind the interpretation of the binomial as a sum of independent Bernoulli. Okay, and when you do cumulative sum, you obtain a new sum with a new parameter. That is the number of terms in my sum. That's why you have exactly the statement of the exercise 22. Okay? But I repeat that it's a good exercise to do at home to try to prove this equality that is exactly equivalent to what I have proved here. The advantage of this solution it is that short, in fact, and I have no computations to do. Okay? But a good exercise is to try to prove the same result with another approach using this and trying to find and to compute this term using the law of total probabilities. Okay? We will see in 1 month, more or less, that in order to handle sum of independent random variables, we will have a more general tool that it is called the moment generating function. That will be easier than this kind of computation here, but we don't have this tool for the moment. Okay. So in the case of the Bernoulli, I have this nice interpretation in terms of sum of independent Bernoulli. You will see next session that in the case of Poisson distribution, but if I want to do the same kind of thing, I have to do the computation using the law of total probability, and I will do. Okay, next session. Okay? So little break, 10 minutes. Okay, so we are going to continue the course, and today we are going to be interested in the expectation of discrete random variables. Okay? So that will be, you will see for us, a kind of generalization of what is the mean for numbers. Okay. So before to define, we are going to introduce some sets of random variables. That will be in fact the sets on which the expectation will be well defined, because you are going to see that an expectation is defined through a sum that can be in fact infinite or even not well defined. So I have to restrict myself to particular cases, in order to compute expectation. So first of all, a little remark, because it's something that we are going to use in the proof of the proposition on the slide here. So it's the following. Okay, so we are going to graph the identity mapping here. Okay? Why not? So it's start from 0, 1, 1, okay. You have here, okay, the mapping f of x equal to x. Okay? Now I want to plot x squared. So x square of 0 is 0, x square of 1 is 1, okay? And in fact, at the beginning, that is between 0 and 1, the square will be below the identity, and then will be greater. So if I want to study the position of x with respect to x square, okay, when I am in the positive case, I have two situations, okay? I will write it, I have one color here. This one, let's say, x square. The square of a number is less than this number if I am between 0 and 1. Okay? And I can continue. X to the power 3, I will obtain something like this. Okay? So, and so on. Okay, so it's a very bad picture, but the idea is just to have the intuition about this fact. Okay? And you are going to see why I plot this one, okay, in a few seconds. Okay? So let's introduce the definition. So we are in the discrete case, okay, meaning that I consider a random variable, and discrete means that the range, that is the set of the possible values, okay, the range is countable, okay? It's the definition of being discrete, okay? So for P belonging to N, I defined the space LP of omega AP. Keep in mind that I start from a random variable and I have initially a probability that is defined on a set A with values in 0, 1, such that, so P is the proba on my universe omega, meaning that P of omega is equal to 1. Okay? So what I will define as LP of omega AP, it's a notation. And if I don't have ambiguities in my statement, it's something that we will define simply by LP, omitting what I have inside, okay? But I keep inside that inside I have a universe. I have the set calligraphic A on which is defined my probability capital P. Okay? And what is this set? It's a set of random variables. So you have inside random variable. It's a set of mapping. So it's the set of X that are discrete random variables. Okay, so I work with discrete random variables. And I want an extra condition to be fulfilled. Okay? So I have my range here. And I have given this notation for the set of the possible values, the xi here. And it's the set of the discrete random variables such that the sum for I belonging to capital I of the absolute value of xi to the power p times the probability that x is equal to xi. So here I have a sum, okay, a countable sum that may be finite or infinite but countable, of positive term. You know that when you have a sum of positive term, okay, I have only two possibilities, plus infinity or finite. Okay, plus infinity or finite. And I want this sum to be finite in this situation. So it's the set of the random variables that are discrete such that, okay, this sum exists and is a finite number, not plus infinity. Okay? And the P you have here, it's the P you have in the definition of LP. Now be careful, it's not the capital P. You have a small p and a capital P. Capital P being my probability and small p being a number. Okay? So you have here, if I take my slides, the number small p that is here, that is present in this expression here, and capital T, that is my probability, that is present here. Okay? So it's a definition. Why not? It's the set of random variables fulfilling one particular condition, that is, this sum is finite here. Okay? With P, that is a power. Absolute value of xi to the power. First remark. First remark. What happens if my small p is equal to 0? What is my sum if small p is equal to 0? 1? Yeah. So this is the sum I am interested in, that I will call, let's say, star. If p is equal to 0, star is equal to what? Well, I have a number to the power 0 that is equal to 1, and I have simply the sum I belonging to capital I, probability that x is equal to xi. Xi being the set of the possible values for capital X. What is this sum here? Yeah? 1. Okay? So it means that L0 is just, in this situation, the set of all the discrete random variables, all of them, because the condition is always fulfilled. The sum is equal to 1, so it is finite. Okay, so L0 is equal to the set of the discrete random variables without any extra condition. So E0 is all of them. Okay? If P is not 0, for example, P equal to 1, I will have a condition. Okay? And we are going to see what happens. Okay? Clear or not? So I define these sets of random variables just fulfilling these criteria. The sum is finite. The sum related to the distribution, the probability mass function, and the set of the possible values, that is xi. Okay? And I just remark that for p equal to 0, this condition is in fact not the condition because it is always fulfilled. The sum is equal to 1, so it is finite every time. Okay? Second question or second remark. If I ask you to compare these two sets, one is included in the other, which one? You have everything on the board here. Of course, L1 is included in L0 because what is L1? L1 is the set of the discrete random variable but fulfilling one particular condition. So of course, it is included in the set of all the possible discrete random variables. So I have this one. And in fact, this little inclusion that is very basic to prove because here I have no condition, here one condition, so of course I have a subset of, L1 is a subset of L0, but it's something that is a consequence of a more general result, that is the proposition written on the slides here. Okay? And in fact, what we are going to prove, and this is the meaning of the proposition 9 here, is that we have the following situation. You have here L0, the biggest. We have seen that L1 is included in L0. That is, L1 is here. And we can continue. L2 is here. L3, and so on. Okay? L1 is included in L0, L2 is included in L1, L3 is included in L2, and so on. Okay? Yeah? Which one? But just take the definition. What is the definition of L1? So here I have the definition of LP. Okay, so it's what? The set of the discrete random variables such that this sum is finite. If I take p equal to 1, it implies that the sum of the absolute value multiplied by the probability that x is equal to xy is finite. So I have, okay, L1 is a set of discrete random variables fulfilling one particular condition. Okay? L0 is the set of all of them, all the discrete random variables. So if I am a discrete random variable that I fulfill a particular condition, I am included in the set of all of them. Okay? I don't know if I said that you have the set of all the mappings, and you have the set of the mappings that are continuous. Of course, the set of the continuous mapping will be included in the set of all the mappings, because I have an extra property that is fulfilled, that is not necessarily fulfilled by all the discrete random variables. Is it clear? Whatever the condition is here, okay? L1 is just the set of the discrete random variable fulfilling a particular sum is finite. L0 is the set of all the discrete random variables. So necessarily L1 is included in L0, because in L1 you have discrete random variables. Maybe not all of them, so I don't have an equality a priori, but just an inclusion. Okay? What is not clear?
The sum being finite,
I repeat another example, okay? So if you have the set of all...
Yeah, I understood your examples, but I feel like you explain the same thing with the same words.
So I can give you another example. You take the set of the natural numbers. If you take the set of the odd one, you have a subset.
Yeah, I do understand that, but I'm not understanding why in this case, why L1 represents something that is in L0.
Yeah. So I repeat, you are okay that the odd number are included in all the numbers? So what are the odd numbers? They are just the ones that are not divided by 2. So it's just the set of the natural numbers that fulfill the particular property.
So I will just ask you another way.
No, just speak with the noise and sorry, but okay.
I will ask you another way. Why is the sum of multiplication of the number with this probability is included in the probability?
Included in the probability? No. The LP spaces are set of random variables. You have inside random variables. So you have inside mappings from omega into R. You don't have probabilities inside. Huh? I just said that with my definition here, what I call LP of omega AP, that is a notation, is a set of discrete random variables fulfilling this particular condition. So you have inside discrete random variables. You don't have probabilities, you have nothing like this, okay? It's just that the P that is in the notation here will be involved in this sum here, in the condition in fact. Okay, so in the LP spaces you have inside random variables that are discrete in this case, okay, that are just mapping from omega into R, fulfilling the fact that the set of the possible values is at most countable. Okay? So I just said that if you take this set of random variables and that you impose a condition, of course you will be included in the set of all of them. It's just what I said for the moment, basically, not more.
But I'm not just visualizing.
You?
I'm not visualizing. How can the L1 be in L2?
I think I also know what you mean by your question, because for me it's also that. I mean, I understand the reasoning that discrete random variables, like the whole set of random variables, has to be bigger than any that has constraints, but
It is bigger than any subset, in fact,
yeah,
yes.
exactly. But what's less maybe visible for us is that why does a sum of absolute value xi to the power of p multiplied by a probability as p goes larger is more
No. For the moment, I don't say this. Huh? We are going to prove this. For the moment, I just take this example, and only this one.
Even at this
No, in this case, it's not the same thing. In this case, it's not the same thing, because in L0, so if I have my condition, I take small p equal to 0 in my condition. In fact, I see that this condition is in fact nothing. It's not a condition because it is always true. So in the case of L0, you have inside everybody. Because this condition disappears in the case where P equal to 0. Simply this case. So I said that when I take L1 included in L0, I just said, in L1 I have discrete random variables that will fulfill a condition. For the moment I don't handle this condition, but a condition. While in N0 I have the set of all of them without any kind of condition. It's just what I said. And now we are going to prove that we have the proposition that my picture hold, but I have to prove this. It's not that clear. This one is clear a priori, okay? For the other, we will have to work a little in order to obtain it. So I repeat, L0 is a set of random variables that fulfill a priori the condition that is written on the slide. This one for P equal to 0. For P equal to 0, this term disappears because it is equal to 1. So the sum of the P is equal to 1, implying that the sum is always finite for P equal to 0. So L0 is just the set of all of them, all the discrete random variables. My remark, and it was just a little remark, I don't prove nothing for the moment, is that if I consider L1, what is L1? L1, I have inside discrete random variable fulfilling this condition for P equal to 1, so maybe it can be fulfilled or not, I don't know, it depends on the random variable, but the only thing I can say is that if I am a discrete random variable and that I fulfill the condition, of course I am a discrete random variable. So L1 is included in L0. It's the only thing I said for the moment.
I think it would, maybe I'm not sure if you understand it already, but I think to just show it intuitively, it would be sufficient to show that one example of X such that it's bigger than infinity.
I think
Then it's clear that it has to be smaller.
the problem is that for me at least, I don't understand why it is splitting and not expanding, why it is like going smaller and why it's not going bigger.
Bigger than the infinity? What are we talking about? This one or this? I don't want to speak about the propositions. Okay? Only this one for the moment. Because it's only what I have said. Be patient. We are going to do this one and I will explain to you why. My explanation is my little picture here. You have x, x squared, x cubed. In fact, you decrease. And not you increase in the case of number between 0 and 1. But, yeah, but be patient. Okay? Yeah, I understand, but we are going to prove and I'm going to explain why. For the moment, I just write on the board this inclusion. I don't write this one, but this one. And this one is just to say that here I have everybody and I have here some of them. Some of them is included in everybody. For this one, I will have to work. This argument won't be valid for proving this one. I will have to work, and it's what we are going to do. But for this one, it was just a remark. And here I say that, okay, it works, but in fact, it's a general fact that we are going to prove now. Okay? It's just what I said. So, since you want, we are going to prove. Okay? So I repeat, clear for everybody, this and only this. Okay? Everybody, some of them. Points. Okay? Now we are going to prove that this special subcase is in fact the special subcase of something that is more general, that is this one. Okay? That tell me that if P is less than Q, LQ is included in LP. I don't say that this result is natural or not. I don't mind. I don't care. We are going to prove. Okay? But my intuition is that I have made a picture and it's this part of the picture. You have x, x squared, x cubed, smaller and smaller. L0, L1, L2, L3. This is the intuition and you are going to see how to prove this. But if you have this, it's the key argument of my reasoning. Okay? So let's do the job. Okay, so in fact I introduced this at the end in order to say, okay, I am able to define what is the expectation in a correct way. It's what we are going to do in the next slide, just before I handle some set of random variables. Okay? So I have this. I erase everything and we are going to write everything in order to see what we have to prove if I want to prove my proposition. Okay? So I erase everything in order to copy it in a different way. Okay? I keep this on the board because it will be my key argument. Okay. If I have a look at my proposition, I have P that is less than Q. Two numbers, P less than Q. Okay? What is LQ? LQ is the set of random variables, RV, okay, in short, such that the sum I belonging to capital I, xi, q, p, x equal to xi is finite. I just copy the definition for the moment. LQ is this one with the power q. What is LP? LP is the same, but with my condition, with my small p here instead of small q. So in other words, in order to prove what I want to prove, that is, in order to prove that LQ is included in LP, I have to prove the following, that is, if I am in this one, that is, if this sum is finite, then necessarily this one is. So what I have to prove is that sum of I, xi, q, p of x equal to xi finite implies the sum I belongs to I, xi, p, probability that x is equal to xi finite. This is my job. If I want to prove the proposition 9, I have to prove that if I am in LQ, I am in LP, meaning that if this sum is finite, this one is. Okay? So is it clear what I want to prove? Before to prove, okay, the first thing that I have to be clear is that what I want to prove. I have the space LP, the space LQ to prove that LQ is included in this one. I have to see that if I fulfill this condition, this one is fulfilled. And I will prove this way that LQ is included in LP. Okay? Clear? What is not clear?
So if the set LQ is included in LP, and this set LQ is smaller than LP.
But included means it's smaller, huh? It's the same, huh? To be included for set means that you are smaller, in fact, or inside, okay?
Yes. So if it is smaller,
Yeah?
how can proving that the sum inside the being finite implies that the sum
No, it's not the same sum, huh? It's not the same sum. I just say that I have a definition for LQ. Okay, so just say to summarize what I want to do without forgetting the sum here. I have a set fulfilling, so it's a set of mapping fulfilling P1. I have a set of other mappings fulfilling P2. If I know that P1 implies P2, the first set is included in the other. That's exactly what I write. Simply. Okay? Whatever the sum is. The sum may be technical or not, okay, whatever. But I said that if I fulfill one property, if I fulfill another property, and if the first one implies the other, the set of the first will be included in the set of the other, for sure. Okay? So it's exactly what I write. So my job now, in order to prove this one, is to prove that if I have this hypothesis, I want to prove that this one is also finite. Supposing this. It's my job if I want to prove that LQ is included in LP. So my hypothesis is this one. I am in LQ. I want to prove that I am in LP. Okay? if I want to prove that I am in LP, I am interested in the sum from I belonging to I, xi to the power p, probability that x is equal to xi. Okay? Now, and that's why I have done this picture, I have a priori a little problem, because if I want to compare this quantity with this one, I have to compare the absolute value of xi to the power p and the absolute value of xi to the power q. And as since in my little picture, it depends. It's not always the same thing. There are cases where I have here x squared and x cubed that are smaller and smaller, and here x squared and x cubed that are bigger and bigger. So I have to consider cases. I have to consider cases. In fact, we are going to cut the sum in two parts. The part where these terms here are smaller, and the part where these terms are greater. And then we are going to work with these two parts independently. Okay? And if you have understood this, after it's finished, in fact, this is the idea. I want to compute power, and to compare power, a priori complicated because it depends. Let's see what happens in each case. So, I write my sum this way. I will write it in two parts. The part where my terms inside here are greater and the other are less. So I can write it this way. So it's the set, okay, of xi to the power p probability that x is equal to xi, but I will do the sum only on the set of the I belonging to capital I, such that the absolute value of xi is less than 1. Okay, I consider the sum only for the ones that are less, but if I do this, I miss some terms. That's why I add the sum, of course, the same thing, the set of the I belonging to capital I, such that, by the contrary, and here I have just written that if I am here, that I have xi that is less, or xi that is strictly greater. It's the only thing that I have said, not more. Okay? That's why I can cut my sum in two parts. The part where I am less than 1 for xi, an absolute value, and the part where I am strictly greater. Okay? And why I do this? I do this because I have this little picture in mind here. I know that if I am less than 1, I have x squared, x cubed. If I am greater, I have the other, x squared, x cubed. Okay? So, in fact, I have two terms in my sum. I have this one, and I have this one. And I remind you that my objective is to prove that if I suppose that this one with the q is finite, this one will also be finite. It's my job. Okay. So, I want to use this hypothesis here. But I said that if the numbers are greater than 1, I know that I am in the situation x squared, x cubed. So, the bigger the power is, the bigger the number is. So in this situation, okay, since I know that q is greater than p for this term here, and only for this one, this is less than the same sum with, instead of power p, power q. Because when my number is greater than 1, according to my picture here, xi to the power p in absolute value will be less than absolute value of xi to the power q. So this sum, the second one, is less than this one because I am in the good situation here. The situation where the power increase and increase my number. And what I know for the second sum, I know that it is finite. It's something that is finite. It's a number. Okay, so I have something that is finite. The only thing I have to deal with is the first. If I prove that the first is finite, it will be okay for me. But why the first is finite? Because this one is less than 1, so this one is less than 1. So this one is less than the sum of the probability that x equal to xi, and I know that, so it's not the sum over all the terms, but in each case I can say that it is less than 1 because the sum of all the probabilities is 1. Okay? So, I repeat. I want to prove that LQ is included in LP. So I want to prove that if the condition in the definition of LQ is fulfilled, that is this one, I want the condition for LP to be fulfilled. That is, this one is finite. So my hypothesis is what I have circled in orange here. So the sum I am interested in, this one, I want to prove that it is finite. In order to introduce what I know, it means that I have to compare the absolute value of xi to the power p and the absolute value of xi to the power q. It depends. If I am less or greater than 1, I have two different things. That's why, instead of doing the things directly, I cut my sums in two parts. I do the sum on the indexes such that the absolute value is less or strictly greater. I have two terms in my sum. Here, for the second sum, I can apply the fact that I am in this situation, so x squared, x cubed, and so on. Q being greater than p, I am sure that this one will be greater than this one. And from my hypothesis here, I know that this sum is finite. So this one is. For the first term, all these terms are less than 1, so this term is less than 1, and then I am less than the probabilities. And I know that the sum of all of them is 1. So I am finite for sure, because I am less than 1. Okay? Question?
Should be also value should be less than more than 1.
No, I have two complementary sets to be less or equal or to be strictly greater.
Now, they should be also constrained.
Yeah, I have what I have written here. Okay, you have the same thing here. You have the constraints that are the same here and here. Okay? But you do the sum with some constraint, and here you know that the sum without constraint is finite, so it is finite in all cases. Okay? Okay?
For example, the second one.
Yeah?
Okay, yeah, you understand.
Okay?
Okay, because yeah, you understand.
Okay, perfect. Without me. Perfect. Questions? So it won't be the main part of this course, it was just to show you how to prove this. To have the intuition that, okay, as we say, the LP spaces are decreasing 1, L0, L1, L2, L3. The idea, if you have this in mind, you have the good intuition on this problem, okay? And you will see that here I am in the case of discrete random variable. It will be the same for continuous random variable or for more complex one, in fact, okay? So I have these spaces, okay, that seems to be strange at the moment because I have a condition with sum and power. I don't understand why I need to have them, okay, and why I need to have them. My objective will be just to be able to define expectation, variance, and so on. And if I want to make this definition correct, I need to be sure that what I define as the expectation or as the variance is a number, not something that is infinite or something like this. Okay, I want the expectation and the variance well defined, and in order to define them in a good way, I need these spaces. It will be L1, if I anticipate a little, L1 will be the space on which the expectation is well defined. So when you have a random variable inside, you will be able to compute explicitly its expectation. L2 will be the set of the random variable having a variance that is a number, something that is a positive number, not plus infinity or something like this. L1 being included in L2, if we are able to have the variance, you will be able to have the expectation. It's just what you need to have in mind. Okay? So it's a little bit technical, but not that, okay? It's just handling sum. And you are going to understand just after why I introduced them, okay? So don't spend too much time on this. It will be crucial for the course, okay? But it's just to define the things in a good way, okay?
This is a very side question.
No, no. Answer the question.
P implies number of moments.
What?
P does imply number of moments.
For the moment, I don't speak about moments, so I don't prefer to anticipate. But I have said a little bit concerning the expectation and the variance. L1 will be related to expectation, as we are going to see on the next slide, and L2 will be related to variance, as we are going to see 2 slides ago. 2 slides, okay? 2 slides. But for the moment, I have this one. I just L0, L1, L2, and so on. Why not? So you will see now, okay, for my definition of the expectation, a definition that for most of you already know, okay, without having defining L1, L2, and so on, okay? But it's just to make this clear. So may I erase the board? Everybody? Okay. You have the proof, in the list of proof, you have this one also that is written, okay? You will have the proof of in the first list of proof, you have the proof of the proposition 9, and you have also the proof of the proposition we are going to see just after, proposition 10, okay? So now I erase this one, okay? And don't need it anymore. Okay, so I define the expectation, and the expectation for the one that are in L1. So remind what is L1. L1 is the set of the random variable such that the sum absolute value of xi, probability that x is equal to xi is finite. What you have here, okay, is just the absolute value of what you have in the sum here in the definition 13. Okay, so it means that if x belongs to L1, but I know that this one is finite, so I have the right, because it's a number, I have the right to write this sum. This sum that can be a sum over an infinite number of index, but whatever, I know that it is correct to write it because this one is finite. Okay? So the sum is convergent, if you remind the definition of being convergent for us. And this sum that is now well defined, if I suppose that I am in L1, is just what I call the expectation. Simply. So when I have the right to write this sum, it is just the expectation. Okay. Little remark. Here I have a sum. My hypothesis is that capital I is countable. Countable means that I have in fact two possible situations. The case where I am finite, and the case where I am infinite, but I am not too much infinite. Let's say infinite as a sequence. This is the definition of being countable. My elements may be represented as the elements of a sequence. In the case where this number is finite, no problem with this. I don't need to define all these things, okay, because I have a sum over a finite number of elements. So typically, for the Bernoulli, the binomial, the uniform, okay, I will have finite sums, so no problem in order to be sure that they are finite numbers. The problem may occur when this one becomes infinite. Typically, in the case of the Poisson or in the case of the geometric, I will have to handle with an infinite sum. So I have to say something, because an infinite sum is not always well defined. Okay, it may be in the case of positive number, it may be plus infinity also, and I don't want this case. Because if I write some algebraic relation, if I have plus infinity inside, okay, nothing works in fact, okay? Nothing works. So it's something that I don't want to. So definition of the expectation, and intuitively, what is the expectation is just a kind of mean. So here you have the set of the possible values, okay? It's a kind of average, let's say, but weighted by the probability to take this value. Okay, so it's a kind of average value for the random variable. Okay, it's a kind of average value that is the sum of my possible values multiplied by the probability that I take this value. Typically, in the case of a uniform, you will see that it is the classical mean. Classical mean. Okay? I can generalize this definition to more complex random variables. You will see maybe next session or next week, at the beginning of next week, that from an intuitive point of view, the expectation is very interesting because it's the number that answers to the following question. You have a random variable, so something that can take a large number of values, okay, in this infinite number of values. If I ask you to summarize the information that is contained in one random variable, that may take a lot of values, but the best possible number in order to summarize with one number what may be this random variable is the expectation. You can't do better in order to summarize what is a random variable is if I restrict yourself to use a single number. A single number. Okay? We are going to see this, the consequence of a little result in these 4 exercises. Okay? So, I have defined the spaces where the expectation is well defined. Now we are going to compute, okay? To see typically in the cases we have seen together that are uniform, binomial, and so on, what are the expectation of these random variables. For uniform, binomial, and Bernoulli, I won't have the problem with is the sum finite or not, whatever, because I have finite sums. In the case of Poisson and geometric, I have to be careful because I will have to deal with infinite sums. Okay? Clear for everybody? So it's exactly what is written here. Computation in classical cases. Okay, so it's what we are going to do now until the end. And I want you to be able to do these computations. Okay? So I erase this one because you have it on the slides, okay? And now my job, or maybe not because instead of the, so here, the expectation of each side. Okay. So let's come back to what we have seen together. We have seen several cases. For example, we have seen the uniform random variable, okay, on x1, xn, okay. So here, typically, I take a finite number of possible values, small n. So the sum involved in the definition of the expectation is the finite sum. I am sure that I am in L1 because I have a finite sum. No problem with this, okay. So if x follows a uniform on x1, xn. Now what is the expectation? Okay, so it's a sum, so it's a sum from I equal to 1 to n of what? Of xi. It's the set of my possible values here, multiplied by the probability that x is equal to xi, that is equal to what here? 1 over the total number of elements in my set. And in this very particular situation, what I call the expectation is just the mean of these numbers. Okay? And for other type of random variable, it's just a generalization of the classical notion of mean you know. but taking into account in the other cases that in general, for other situations, you don't have the fact that the probability to take a value is the same for all the possible values. It is the definition of the uniform. Okay, if I change this, okay, I will change the definition of my expectation here, okay, or the value of my expectation, but keep in mind that what I have in this situation that is just to obtain the mean is a very special case or the more basic case for the definition of the expectation. Okay? So I have this one. I can continue. If I want to continue, I need to precise the values. So for example, a little subcase, if I take x1 equal to 1 and xn equal to n, why not? Okay, so meaning that I have a uniform on 1, 2, 3. I take x1 equal to 1, xn equal to n. Okay. In this situation, I have a uniform on 1, 2, 3, n. If I want to compute the expectation, it's something that I have already done at the beginning of the session. It's 1 over n, the sum from I equal to 1 to n of I. And here, we have seen that it is nn plus 1 over 2. So here I obtain n plus 1 over 2. That is just the middle of the interval 1, n. So I repeat what I have said. This is that if I don't give you the particular values, x1, x2, xn, you can't continue the computation. But if I give you some special case, in general, you are able to continue the expectation. Typically, if I take for x1, xn, 1, 2, n, okay, but you obtain exactly this for a uniform on 1, 2, until n. Okay. The Bernoulli. So are you okay with this? Bernoulli. Bernoulli, very, very basic. I have two values, 0 or 1. Okay? So in the case of Bernoulli, I can say x0 that is equal to 1 and x1 that is equal, x0 that is equal to 0 and x1 that is equal to 1. I have only two possible values. So in the case where x follows the Bernoulli of parameter p, in my sum I have only two terms. And I obtain 0 times the probability to be equal to 0, that is 1 minus p, plus 1 times the probability to be equal to 1, that is p, and so I obtain the expectation of a Bernoulli of parameter p is p. Okay? So to continue in this case here, suppose that x is equal to the indicator function of a subset of omega here. If you come back to the slides concerning the Bernoulli, I have done a little remark in the class. Look at me in the slides here. That an indicator function in flight follows a Bernoulli. Okay? So x is equal to the indicator function of A. What is the expectation of x? No. It's 1 when A is equal to, for A equal to omega it works, not for A in general. No. For A equal to omega it works. You have 1, but if you have A that is strictly included in omega, a priori it doesn't work. We have seen together, so come back to what we have done together during the previous session. I have proved that an indicator function follows the Bernoulli of parameter p of A. So the expectation of Bernoulli being the parameter, the expectation of an indicator function is just P of A. This remark is important here because you see that in fact the notion of expectation is in fact something that generalizes the notion of probability. In the case of an indicator function, expectation and probability coincide. It's the same thing here. The expectation of an indicator function is P of A. If you change x to be more complex than an indicator function, you have an extension in some sense of what is P of A. Okay? So I have this one. So for the moment, I'm very basic because I have nothing to compute really. I just have to write the formula. Okay, and the computation are not complicated here. So are you okay with this case? Okay? Continue. The binomial. So when I have the binomial in mind, okay, I have said to you that you always write the following little formula. That is, in the case of a binomial, so here you have the definition of the expectation. In the case of a binomial, I have used A plus B to the power n, that is equal to the sum from k equal to 0 to n, c n k, a k, b n minus k. Okay, when you have binomial, think about this relation. So in the case of the binomial, once again, I have a finite sum to compute, finite one. Okay, so the expectation, so when x follows a binomial of parameter n and p, by definition, the expectation of x, that is just a finite sum here, is a sum from k equal to 0 to n. Of what? The set of the possible values that are by k equals to 0, 1, 2, and so on. So I have k, c, n, k, p, k, 1 minus p, and minus k. Okay? And in fact, it's a computation that is not very far from one exercise we have corrected together in the summer list. In the summer list, I have asked you to compute the sum of the k, c, and k. We have done the job together. And the idea was, I start from the relation that is the basis of the definition of a binomial, and I want to make the k appear. In order to make the k appear, I compute the derivative of this expression with respect to a, in order to make the k from here to here. So if I do the job, it's something that I have already done, so I write, so I compute the derivative of this term here. So that gives me n, a plus b n minus 1 equal to the sum from k equal to 0 to n, c n k, k, a k minus 1, b n minus k. Or the only thing that is a little bit different in what I want here is that I don't have something to the power k minus 1, but something to the power k here. So it means that in my expression, so I obtain this equality computing the derivative of this equality here with respect to small a, something that I have already done, so that's why I don't spend too much time. I have done this during the previous week, okay? And if I want to make appear ak instead of ak minus 1, what I can do, I can multiply by a on both sides here. I have the right, because a doesn't depend on the set of indexation. And so from this formula, here I have a to the power k. So what I have to replace, I have to take a equal to p and b equal to 1 minus p. And if I do the job, I take a equal to p and b equal to 1 minus p, and I obtain n times p. The expectation of binomial of parameter n and p is just the product of the parameters. It's just the product of the parameters. And the way to obtain, I repeat, you come from this relation that was the basis of the definition given in the slide here. I compute the derivative with respect to a. I obtain the white term here without the multiply by a. And in order to make appear the term I want, I multiply by a on both sides, and I obtain that this sum is exactly this one, where I take a equal to p and b equal to 1 minus p. So I obtain n, 1, p, and p. Okay? We will see in a few seconds another way to obtain this result, okay, without doing this computation here. But I need an extra property concerning the expectation to be able to. So for the uniform, I have the average. For the Bernoulli, I have the parameter. For the binomial, I have the product of the parameters. Okay? Do you agree with my computation? So if I continue, so I have the geometry, but I will do first the Poisson. It's simpler, and I will finish by the geometry. So I erase this one. So are you okay for the uniform, the Bernoulli, the binomial? It's okay? So for the Poisson. So here I am in the situation where, okay, x of omega is equal to n. So I can take here an infinite number of possible values. And the probability that x is equal to k is equal to exponential minus lambda, lambda to the power k over k factorial, lambda being strictly positive. Okay? So now, okay, but I have to be a little bit careful because I have an infinite sum here. And that is not convergent a priori. So I have to check what happened. You see the difference between this case and the previous ones. Here, the set of my possible values is infinite. Okay? So I will have an infinite sum of positive terms. It can be finite or can be plus infinity. In this case, it won't be complicated to compute directly the things, but let's see what happened. So a priori, what I want to compute in this situation here is to compute the sum from k equal to 0 to plus infinity of what? The possible values that are the k multiplied by the probability that x is equal to k. That is equal to the sum from k equal to 0 to plus infinity of k exponential minus lambda, lambda to the power k over k factorial. The first thing that you can remark, okay, I just replaced the definition of the distribution of x inside this sum. The first thing that I can remark is that I have a k here. So the sum doesn't start from 0, in fact. It's a sum. I can write it for 0 or 1. It gives rise to exactly the same thing because the k is for, and the term for k equal to 0 is equal to 0. Okay. So do you have an idea what to do here?
I think you can just factorial k should be from the k to this one and change some. It would be 1 or something.
So I just remarked that what is k over k factorial?
minus
1 over okay, I'm agree. So if I have a look on the sum I am interested in, sum from k equal to 1 to plus infinity k exponential minus lambda to the power k over k factorial can be written as the sum from k equal to 1 to plus infinity exponential minus lambda k over k minus 1 factorial. Okay, so something that is not very far from the general term of the distribution, the probability mass function. The only thing that's changed a little is that I have exponential minus lambda, okay, but I have 1 over k minus 1 factorial instead of 1 over k factorial. So what can I do? There are several possibilities to do, but I can change my index in order to make k factorial appear here. So I can write it as the sum from k equal to 0 to plus infinity. I change my index, exponential minus lambda to the power k plus 1 over k factorial. I change k minus 1 into k. I do a translation of my indexes, okay, in order to obtain this sum here. But it's not very far from what I want because what is this sum here? 1. And in fact, it remains a lambda. So this sum is equal to lambda. Because the sum I have circle, okay, is equal to 1. Because it's the sum of all these probability mass function. Sum equal to 1. Okay? So once again, here the expectation of a Poisson of parameter lambda is lambda. Okay? So something very, very easy to keep in mind. Okay? The expectation of a Poisson of parameter lambda is simply lambda. Okay? So let's finish with the geometric if you don't have questions. So here the idea is that it's a very particular situation. A very particular situation where when I multiply by k, I see that I can simplify the k and the k factorial. In general, it's not the case, but here I see a possible simplification. Let's use it to see what happens. Okay? Let's use it to see what happens. Do you agree? So if you are the last case, that is this one. The case of the geometric distribution. And in the case of the geometric distribution, I remind you that I replace this little trick here by what? By the fact that the sum from k equal to 0 to n of x to the power k is equal to 1 minus x n plus 1 over 1 minus x if x different from 1. We have seen together that I can pass to the limit if I suppose the absolute value of x to be strictly less than 1. Okay, so it's what I have to keep in mind because it's what we are going to use in order to compute. So may I erase my blackboard for the computation of the Poisson? Okay, so for the geometric, what I have the probability when x follows the geometric of parameter p, the probability that x is equal to k is equal to what? It's equal to p 1 minus p to the power k minus 1 for k belonging to n star. I have this one. So a priori, the term I am interested in, if I come back to the possible definition of the expectation, okay, I have to check if this sum is finite or not, but what I will be interested in will be the sum from k equal to 1 to plus infinity, k, p, 1 minus p to the power k minus 1. I have to prove two things, the fact that this sum is finite or not, and if it is finite, to prove how to compute it. Okay? It's what I have to do. Here I am again in the situation where the number of possible values is infinite, so I have an infinite sum. I am not sure that this sum is finite or not a priori, okay, so I have to work a little. And we are going to use this. Once again, I have something to the power someone, okay, and I have to make a k appear. So what can I do? I compute the derivative. So I have a relation here. I can compute the derivative and see what happens. So let's do. I have an equality. F of x equal to j of x. Let's write f prime equal to j prime. So from this one, I obtain what? I obtain that the sum from k equal to 0 to n of k x k minus 1 is equal to 1. So I am happy to have this because I have the k, I have the power k minus 1, so I have almost everything. Okay? It's equal to what? By the derivative of a ratio, u prime v minus u v prime over v square. Okay? So let's do minus n plus 1 xn 1 minus x minus 1 minus x n plus 1 minus 1, so we have a plus, over 1 minus x squared. I have computed the derivative. I have computed the derivative, u prime v minus u v prime over v square, a classical formula, okay, so do it at home if it's not clear. U prime, we just check that I don't have done mistakes, u prime v minus u v prime is okay, over v square. Okay. So if I want to compute this kind of term, okay, I have to see what happens when n goes to plus infinity. Okay? So if I want n goes to plus infinity and being convergent, okay, I have one condition on x to obtain this, okay? So if the absolute value of x is strictly less than 1, what I have here, because p is a number strictly between 0 and 1, so what I have for this sum converges when n goes to plus infinity toward the sum from k equal to 0 to plus infinity to k x k minus 1. And what happened for this one here? What happened for this one? So keep in mind that the absolute value of x is strictly less than 1. So this one goes to 1. What happened for this one? 0. I have plus infinity and 0, but here I have something that is, okay, an exponential convergence, while here I have something that is polynomial. So the best is this one, okay, the geometric sequence. If you multiply by any type of polynomial in capital N, you will converge towards 0 without problem, okay? So it means that all this one is 0, this one is 1, so it remains just 1 over one over 1 minus x squared. Okay? So let's use this one. So I have the equality between both here. So I have This one I have computed. This one is equal to, so it's with x equal to 1 minus p, so I have 1 over 1 minus p squared, that is 1 over p squared, multiplied by p, that is just 1 over p. So the expectation of a geometric is just 1 over p. So expectation of a uniform, that is just the mean, expectation of a Bernoulli, that is p, expectation of binomial, that is np, expectation of the Poisson, that is lambda, expectation of the geometry, that is 1 over p. Okay? So you have this classical computation, and in general, okay, if you are able to compute this one, okay, you are able to compute more or less everything because the ideas are, let's say, the same here. Okay? So we have the computation of the expectation in our basic cases. Okay? So what I have written in the remark here, the classical computations.
So,
Yeah.
how did we go from here to here?
You see that you have this one?
Yes.
Okay, you take x equal to 1 minus p in order to obtain exactly what you want here. You take x equal to 1 minus p and you obtain exactly this one. Okay. So next session, well, it remains to do a few things concerning discrete random variable. I will do what? So I will introduce some properties of the expectation defined as we have seen today. Defined as in definition 13. We have some special properties fulfilled by the expectation. So I will spend time at the beginning to remind them. Okay, so I won't do the proof of most of them, but the proof is in the list of proof 1 in my website. Okay, so we are going to see this in details. I will define the variance and discuss a little bit. I will do, or want to do, I don't know, the classical computation, because if you are able to compute the expectation, to compute the variance, I will say when it will be finished, okay? I will compute the variance in classical cases, and I will just finish by what happened, not in the case of one discrete random variable, but in the case of two, in order to pass from a single random variable to a vector, because in the one part of the course I have to deal with the random vectors that are just vectors where as coordinates I have random variables. Okay? And it will finish the course concerning discrete random variables, and we will do exercises from the list 4. Okay, so a priori, except concerning computation of variance, you are able to do more or less all the exercises of the list 4, and typically the ones that are listed at the beginning of the list, except the one with the variance inside. Okay? No questions? Is it okay? So see you next session.